Welcome to my topic. So it's time to talk about the Container Runtime Interface. And today I'd like to talk about how we use Container Runtime Interface to integrate the hypervisor-based container to Kubernetes. And I'm Harry. I previously worked for VMware and I'm Pivotal, and I'm also a research assistant in Zhejiang University. And now I work for Hyper, and I'm a project manager and feature maintainer for Kubernetes project. So let's start from a survey when I was reading PhD. So it's about the container boundary, and the question is quite simple. Are you comfortable with Linux container boundary? So there are two kinds of answers, actually. Half of them is like they use containers in their provide or safe environment. So another half of the answer is no, because they are using container, for example, trying to serve in the public cloud or in a multi-tenant environment. So as long as we care about this kind of security, so a lot of people, they have to wrap their containers inside full-blown virtual machines. This is actually what most of the container cloud provider is doing today. But in that case, we will actually lose the so-called cloud-native deployment. For example, we have to tolerate the slow startup time of the virtual machines, right? And we also have to tolerate the huge resource wasting caused by your virtual machine cluster in your data center. And on the other hand, every container in your cluster actually have to pay an extra memory tax because there's an extra hypervisor layer running in your data center. So this is a problem. And that's why we have HyperContainer project, because we are trying to first being secure and keep the cloud-native features. So let's begin to revisit the container. For example, for Docker, and we can actually divide the container into two parts. The first part, we can call it the container runtime part, is actually the dynamic view and the boundary of your running processes. For example, in Docker, it is implemented by a group of namespaces and restricted by using C groups. So in this example, your application process, which is echo hello, is running inside a sandbox, which is isolated by namespaces. And the rest part of the container, which we can describe it as container image, is actually the static view of your program, your data, your dependencies, files, and directories. Anything you need to run your application, actually. So in Docker, you will have, first of all, the read-write layer, and then a init layer, so that you can modify the contents in your host files, and then a group of read-only layers, which are usually mounted together to form the so-called Docker image. So that is a container. So this picture actually remind us what happens if we replace the container runtime part to hypervisor-based. So that's HyperContainer. The HyperContainer is actually composed by three small projects. The first one is the OCI-compatible hypervisor implementation, which name is the Runway. And another project is the HyperDaemon. It is our own control daemon. And we also have the very important project, which name is HyperStart. And it is the init service inside this small, lightweighted virtual machine. And the reason we need it is that we cannot start a virtual machine just with your application process as the first process, right? So that's why we have HyperStart. And we need to deal with things like, for example, the execute command, the attach, port forward, things like that, the streaming API. We need to have the engine inside. And another example is that HyperStart will be responsible to manage the user containers inside this HyperContainer, this pod sandbox. So that's why this project is very popular, and we also reached agreement with Intel Clear Container. They are also using our this small project as their init service. And for the Docker image part, however, we follow the standard Docker image implementation, and in the future, very soon, we will support the OCI image. We have a maintainer in OCI. So yeah. That's HyperContainer, and you can see actually the idea is about how to combine the best parts of virtual machine and container. So first of all, it will be portable and behaves like a Linux container. So you can just, for example, start the application by using a hyperctl run blah blah blah, and that container, actually a virtual machine, will be started within seconds, and it only costs 10 or more MB memory extra for hypervisor part. And on the other hand, it is actually using hardware level virtualization with an independent kernel. So if you execute a command inside that container, you will see there's an independent guest kernel running, totally different from your host machine. So that's HyperContainer. And the other thing I need to mention is that HyperContainer actually naturally matched to design a pod. Just check this example. Normally, for example, when you are using Docker, so there's no pod anymore, actually. Pod is a logic concept in any kind of container runtime implementation. But in Hyper, it's not that case. You will have a so-called pod sandbox running, a physical sandbox running, which is implemented by lightweighted virtual machine. And your applications will be running inside this sandbox like normal containers. But please note, we don't have Docker daemon running inside. We just use namespaces to set up user containers inside. So you can see here the pod. And that's why we began to thinking about bringing the HyperContainer to Kubernetes from the very beginning. But at that time, we do not have Container Runtime Interface. So we have to use a volatile internal interface defined by Kubernetes, which is exactly what Rocket was using in the past few years. So in that case, we have to add a Hyper package inside the Kubernetes code base. And we have to implement everything the Kubernetes need to run container, to run pod, every details, including the lifecycle and the pod lifecycle, the containers, the network plugin, the volume plugin, mount volumes, everything we need to do inside of this small package. So you can see it's very complicated. And on the other hand, there are some limitations of Hypervisor. For example, we cannot support the host network, right? It's a totally different thing. So that's why we cannot merge this Hyper package into the upstream Kubernetes. So we have to maintain our own branch. And every time we need to do the rebase, it will become a nightmare. Nobody likes that. So that's why since 2015, I think, we began to propose a so-called client-server mode runtime to the Kubernetes upstream. And thanks to the work by Brandon Burrs, we finally reached our goal. That's why we have the so-called Container Runtime Interface. And since that time, we don't need to have to fork Kubernetes anymore. So the Kubernetes project we had before will finally transfer to a repo which only contains the necessary plugins like network plugins, volume plugins, and these third-party resources. That's all. And we now have our own implementation of Container Runtime Interface, which is Franklin project. I will talk about that later. So let's begin from a container runtime. So the CRI is actually an interface, a group of interface to describe what Kubernetes expect from a container runtime. For example, I am Kubernetes, and maybe you are Docker. So I can say, hi, Docker, please prepare an API which name is start container. So I can pass you with a group of configurations, and you use that to start a container. So that's it. But as a Docker, you cannot say to me, hey, Kubernetes, I have an API which name is swarm mode. Would you like that? As a Kubernetes, I can say, no, I don't need that. So that is the responsibility of Container Runtime Interface. It will help you to narrow down what is needed to implement a container runtime for Kubernetes project. And the second thing is that a CRI is imperative container-centric interface. So maybe you are curious, why not pod? Well, there are two kinds of problems here. So first one is, in that case, every container runtime implementation have to understand the concept of the pod. Well, for Rocket, maybe it works, but for Docker, it's impossible. So that will leave us a burden to implement everything about the pod in the shim, in the runtime machine, for example, in Docker shim. You have to care about that. That's not very good. And the second thing is, in that case, you have to change the container runtime interface every time when there is, for example, a new feature added to pod level. For example, the pod level, we added a new field to the pod specification. Then maybe we have to change the container runtime interface. And we all know that the pod specification actually changes a lot on Kubernetes upstream. So that's also not good. That's why we use container level interface in CRI. So the benefits are very straightforward. There is extensibility, and of course, we can have feature velocity because now, for example, developers in Hyper, in Rocket, they can focus on their own implementation, do not care about too much things about Kubernetes and Kubernetes. And most important thing is that there will be code maintainability, so we don't have to use that volatile internal interface anymore. And I need to say that kind of thing really tortured everybody in the SIG node for a long time, so we don't need that anymore. For more details, you can check this pull request by Fisker, my colleague, and all of the implementation about CRI there. So the container runtime specification is actually quite simple. It's just a group of functions. So you can see there is management for pod sandbox, first of all, and for container, and we have streaming API, and for image. It's quite simple. So you may be curious, what is sandbox? Is it a pod? No, it's not a pod. The sandbox actually describes how you can implement how you can isolate the pod environment. For example, in Docker, it should be infra container with a group of so-called pod level C groups, that's all. And in Hyper, however, it will be a lightweight virtual machine. So it's about how to implement that kind of isolation there. It's not about the pod. And for the container part, however, there is nothing special. For Docker, it can be directly mapping to the Docker container. And for Hyper, it will be mapping to a group of namespace containers controlled by the Hyper start, as I mentioned before. So now we have Container Runtime Interface. We have a group of definitions about what it can do. So how can the CRI work with HyperContainer? So it's quite simple, just implement it. That's why we had a FrankT project, which is now an official Kubernetes sub-project and has been released with Kubernetes 1.6. It has already passed 96% of the node end-to-end performance test, and in the next few days, we will reach the goal of 100%. And we are using the CNI network here, so everything is exactly the same as you are using today. And we also support the pod level resource management, and we also support the mixed runtime on the same node. So you can run HyperContainer with Docker and on the same node freely. And of course, we can deploy FrankT with Kubernetes by using kubeadmin. And in the future, we also have unikernel support, which is now official topic for the Google Summer Code in this year. So please stay tuned. So first of all, how FrankT works, it is actually quite simple. We can see Kubernetes at two parts. The first part is the so-called control panel, the management node. So this is where the scheduling and workload orchestration actually happens. And this is also where the concept of the pod is actually played in the most important role. But however, we also have a node where the Kubernetes is running. So in that place, pod will be transferred. For example, the Kubernetes will watch the change of the pod list in etcd, so it will notice what happened. For example, if the pod is created, so the Kubernetes main cycle loop will deliver its pod to so-called generic runtime. And generic runtime is responsible to generate the configurations of pod and containers. And then it will call the container runtime interface functions to use that parameters to start the pod sandbox and container. So from now on, from that place, from that line, there will no pod anymore. There's no pod anymore, only sandbox and containers. So please note here. And after you call the container runtime interface, the implementation will be responsible for doing the rest of the things. For example, if you're using Docker, there will be a Docker stream running. It will translate the CRI into the Docker API. So it's like a broker. So that's how we implement FrankT. It's just like another broker which is responsible to translate the CRI into the HyperDaemon API. So quite simple. Well, now it's a key point how to implement this kind of runtime scheme, like Docker scheme, FrankT, CRI-O, Workloads, everything. Okay. The most important thing is lifecycle management. For example, if you are using a pod, creating a pod which is named full and with 2 containers inside, so the workflow is like, first of all, run pod sandbox, and then create container A, start container A, and then create container B and start container B. So this kind of workflow, however, in the Docker runtime will be like this. So the run pod sandbox in Docker is actually mapping to start a special container, which named in the infra container. This container will be used to hold the network namespace of the whole pod. And then you will call Docker to start 2 containers for you, and then join those 2 containers to the network namespace of the infra container. So that's how it works. So you can see here, you will actually start 3 containers for this pod, right? But for Hyper, it's not that case. In Hyper, you will, first of all, the run pod sandbox will create a lightweight virtual machine for you. And then you will create and start a container A inside and start a container B inside, so done. There will no such kind of infra container running inside, and you will have a lightweight virtual machine with 2 containers. So that's why I mentioned before, HyperContainer is actually a better implementation for the concept of pod. And for container part lifecycle, however, there's no difference between Docker and Hyper. So for example, if you call the create container, and the container state will be transferred to now to create it. If you call start container, it will be transferred to running, and so on. So this is the first part. And the second part is streaming. So streaming is, I think, the most complicated part for any kind of container runtime. And in the old version, when we have no container runtime interface, we implement things like this. So if you are running, for example, the kubectl execute, and the API server will be responsible to update a connection to Kubernetes, and then Kubernetes will be responsible to send the streaming API to the runtime machine, like Docker tools or Rocket. So you can see here there will be 3 kinds of connections established, but you can also see here there are some problems. So first of all, Kubernetes will actually become the bottleneck. And on the other hand, you can also see here, the runtime machine is also standing in the critical path of this API call. So this actually brought us with severe performance problem when there are a lot of streaming API running at the same time. And on the other hand, there are a lot of code duplication among the runtime machines. For example, Docker and Rocket, they are almost handling this kind of streaming API in the same way, but they have to implement everything on their own side. No code share here. So that's why in Container Runtime Interface version, we changed the design of the streaming. The basic idea is quite simple, that we will start a separate streaming server running instead of handling everything by Kubernetes or the runtime machine. So there's no business for Kubernetes anymore. This server will be responsible for handling every streaming request. And let's see how it works. So again, the API server will send a connection to Kubernetes, and this time Kubernetes only calls the Container Runtime Interface to the runtime machine to launch a HTTP server, a standalone HTTP server, and it will return the URL of this streaming server back to Kubernetes, and then trigger a redirect response to API server. So from this time, the API server will establish a fresh new connection to this streaming server. So there's no business of Kubernetes anymore. And this streaming server will be responsible to handle all of the streaming requests happen next. And that's how Frankly works today, actually. And the Kubernetes will call the CRI execute API, and the Frankly runtime service will be responsible to return the URL of the streaming server. And then API server will establish connection to the streaming server. But please note, why the streaming server can handle this streaming request? That's because as an implementation of CRI, we are responsible to implement those 3 streaming runtime functions, only 3 functions. And what's more important, CRI has provided us with a very useful common streaming library to use, including the HTTP server part, the handler part, the registration part. So we don't need to take care of this streaming server. We just focus on how we implement these 3 methods. That would be much simpler, right? So that's how streaming works. The third thing is the pool-level resource management. It is very important in the Kubernetes 1.6 because it is how we enforce the QoS classes and eviction in Kubernetes. And that is actually the core idea of the borg. The core idea of the borg is that we should mix deploy different kinds of workloads with different priorities in your cluster, so there can be preemption. So that's why we have 3 kinds of QoS classes in Kubernetes. So first of all, guaranteed and bustable and best effort. Here is the example of the bustable pod. And you can see here it has a resource request and resource limit, and they are not equal. So that means this pod can use more resource than its resource request because the scheduler only knows about request. So that's why it's called bustable. And the Kubernetes implemented this model by using the so-called pod level C groups. So like the example here, this pod, when this pod is created, Kubernetes will be responsible to calculate a summary of, for example, the memory limit of all the containers in that pod and calculate summary and write this value into a special C group root on the machine. So if you write the value to memory limit in bytes here. So that's how pod level C group works. And this is very useful for the resource counting. So the outside system can read this value. And it also important for charge container overhead to the pod instead of a node. Because, for example, the streaming server I mentioned, so in the future, we will start a streaming server inside this pod level C group. So it cannot consume more resource than the pod is allowed to do, right? And it's also the case for the container edition, which is created by Docker. So it's very useful. And this kind of model should be supported in Frankly. But I think you might realize that Frankly does not need to use this C group for pod level management. But please note that you cannot start a virtual machine without resource limit. It's not like the container. So every resource limit should be set before this pod sandbox starts. So that's why we need to read the value from these pod level C groups. So for example, we will read the memory in bytes as a virtual machine, as a memory of a virtual machine. And we will also read the CPU quota to calculate a virtual machine CPU number for later use. And you may also find that if any of these values are not set in the pod, we have to use default value, and that's not good. So we encourage people to set a resource limit if they want to use a HyperContainer as a runtime. So that's the resource part, and the next thing is the network part. And actually, just a few months ago, this is impossible because the CNI is still evolving, which cannot support the virtual machine. But now it can do that. And but please note, you cannot start the virtual machine before. You cannot start a virtual machine without a network configuration and set up it later. It's not like container. You cannot, for example, join the container to another namespace or use ns enter to inside to configure the network. It's impossible for the virtual machine. So here is our workflow, which is a little bit different from the standard CNI network flow. So first of all, we will create a network namespace for sandbox. This is a standard CNI network plugin workflow. And we will also call the plugin setup post method to configure its namespace. This is also the same as CNI, but the next thing is different. We will read the network information from that namespace and cache it. So this kind of information looks like this. So that, for example, with interface name, and MAC address, IP address, gateway, and bridge name. So we will read this kind of information from the namespace, and we will checkpoint the namespace path for future usage. It is actually teardown. And we will use this cache network information to configure our sandbox virtual machine later. And we will also keep scanning the CNI network configuration directory to update the cache network information. And that's how it works. And after you have configured the network of this virtual machine, this pod sandbox, the rest of things is just like container. For example, this pod will also have a default interface inside, and it connects to the pair device outside. And this actually is through the tab device of the virtual machine. So nothing special. And the rest of the thing I need to mention today is that FrankT actually supports more runtimes than Hypervisor. And that is majorly because there are some workloads that cannot be handled by Hypervisor. For example, the privileged mode of a container. And also the host namespace. For example, the host network, host PID. And there are also some cases that users just don't want to use Hypervisor. For example, they maybe require better performance or things like that. And on the other hand, the SIG node have also reached an agreement that Kubernetes should not be responsible to handle this kind of a mixed runtime because it is too complicated to implement in Kubernetes side. It will break the current model of Kubernetes. We need to refactor everything. So that's why in FrankT we support mixed runtimes. Any container which claim to use a host namespace or privileged node or have the special annotation will be running automatically by using a built-in or vendor Docker shim. So this Docker shim will also use the same CNI network plugin. So the Docker container here and the HyperContainer can communicate with each other. And this also enable you to mix around your microservices with legacy applications because HyperContainer will provide you with an independent kernel. So any applications which can be running in your virtual machines or physical machines can be migrated to HyperContainer very easily without extra effort. And at the same time, you can also run your newly created microservices in Docker at the same time on the same machine. So that's good. And it also enables the so-called high resource efficiency model, which is mentioned in Borg. So anyone remember the core idea of Borg? Yes, it encourages you to deploy mixed workloads with mixed priorities inside. So for example, in this case, you can just run your critical pod in your HyperContainer, the guaranteed pod. So it will be protected and isolated by using the hypervisor from the noisy neighborhoods. And on the other hand, you can also, at the same time, running your best effort pod or bustable pod in Docker runtimes. So they can be evicted or preempt in the future very easily. So that's how FrankT works. But FrankT is actually only a part from the whole picture if you really want to use Kubernetes in a multi-tenant environment, because we need to deal with the multi-tenancy, the isolated network, the persistent volume. That's why we established the Hypernetes project, which is fully open sourced. So the architecture of Hypernetes projects is quite simple. We just make use of some existing projects like, for example, the Keystone. We use Keystone to manage our multi-tenancy. And we have our top-level resource, which name is network, and the tenant to network mapping is one-to-n. And for network part, it is actually, the network is mapping to the neutron pod. So the Kubernetes will be responsible to call the method like setup pod, and this request will be delivered to a small daemon running in your machine, which name is the Kubistank. So it is a broker between Kubernetes to the neutron API translator actually. And for persistent volume part, which is more easier because we are using Hypervisor for sandbox, right? So we can directly attach a block device like a standard volume to this sandbox and done. So that's why we modified standard plugin to do that. And this is actually what is supporting the hyper.sh. Now we have Kubernetes 1.6, the CRI has become released, the Frankly has become an official project. So now we are actually refactoring Hypernetes to use Frankly directly. And we will also change this Kubistank daemon to standard CNI plugin. And we will also use Flex volume plugin to replace our own standard volume plugin. And we will use TPR to manage our network. And we will use the RBAC with Keystone plugin for the multi-tenant part. So for anyone interested in this project, please pay attention to our Hypernetes repo. Well, so let's reach the summary part. And today, what I'm talking about is actually about the Container Runtime Interface. And it simplified the most tricky part of Container Runtime integration work. For example, it eliminates the pod-centric runtime API in Kubernetes. And it also defined a very clean runtime lifecycle, including the pod sandbox, the container, the image API. It's very good. And it also provides us with some interesting tools, for example, the checkpoint, for us to store some auxiliary data in the runtime machine side. So we don't need to call API server or Kubernetes to get this information or write a temporary file on the node to record those data. And for the streaming part, it's much better because it actually leaves the implementation to the runtime machine. So all depends on how you implement this kind of stuff. And it also provides us with a common streaming server library, so there's no too much burden on our implementation side. And today I also mentioned the so-called Hypernetes project, which actually, I mean, it is the Kubernetes plugin that makes the re-innovation possible. For example, the third-party resource, we use that to manage our network object. And the CNI network, I need to say it's really simple because we just need to implement two methods there, and it is very powerful. And on the other hand, we've also investigated the container network model, but we need to say it is impossible to use that for runtime other than Docker, and it's a pity. And that's why we say Kubernetes is a very great project because it actually enables more possibilities. And that's also, so if you are asking something that can work, maybe you can use SwarmKit for that. But if you are finding something that you want to build your own distribution system like Hypernetes on top of that, you want to rely on that, you want to use something as your dependency, I say it should be Kubernetes. And that is also why I think the success of Container Runtime Interface is actually the success of orchestration project itself. It is because the users of Kubernetes or things like that should never care about the details of runtime stuff. That's why I think Docker has donated the container D to CNCF because it also realized that fact. Well, users should never care about the runtime things. Well, thank you for coming, and this is the end of my speak. So, any questions? Any questions? Can raise your hand. Yes, please.
What end-to-end tests are not passing, actually?
Oh, what? I don't understand.
What end-to-end tests are not passing?
Oh, yeah. Actually, there is a bug inside the hyperdaemon. So actually, most of the failed end-to-end test is caused by that they are using some images from Google. And those images are different from what we are using today. For example, there is no path. There are no paths defined in their image, or their binary path is different from the normal places and things like that. So we need to deal with the special case in HyperStart. So we have sent a lot of patch to HyperStart to deal with that. Yeah. Okay, seems very good, and thank you very much for coming.